even for the application. Let me just say, got it here. Okay, so I'm going to talk about effective cones of rational surfaces. My purpose is to give some panoramics of recent results and then focusing on some blowing up of toric. Then, okay, so let me introduce X is a normal projective variety. From now on, it will be defined over an algebraically closed field of any characteristic. And the effective cone of X is the cone of generated by classes of effective divisors. It lives in this N1 of R, but it can also live in the peak of R whenever the irregularity of the variety is 0. The closure of this cone in the Euclidean topology is called the pseudo-effective cone. It is denoted by this, and I will often talk about polyhedral cones. This means that the cone is generated by finitely many vectors. Okay. So a few general questions about these cones are, sorry. First of all, I wanted to say something I forgot. If X is normal projected in Q factorial, then this pseudo-effective cone has to contain the following light cone. So Q of X is the cone of classes of self-intersection greater than or equal than 0. This is a cone with two parts, and one selects just the part which has positive non-negative intersection with an ample class H. Then eventually, I mean, it is possible to show that the definition of this Q of X does not depend on the choice of this H. This is called the light cone. By Riemann-Roch, this light cone is contained in the pseudo-effective. This will be quite important in what I'm going to say after. So, having this in mind, a few questions are the following. All of them are open. So, first of all, which surfaces do have a polyhedral pseudo-effective cone? This is mostly unknown, and we are going to see some criteria given by Nikulin on this, some results, but this is widely quite open. Then, are there surfaces which contain negative curves and whose pseudo-effective cone has a circular part? So this question is about the possibility of having a mixed behavior for such a cone. And the circular part, of course, is coming from this light cone Q of X. To what I know, this is an open question. And last question, very hard also, assume that X has a polyhedral effective cone, then what can we say about the pseudo-effective cone of the blow-up at one point? So I'm going to say something about the three questions, but without any complete answer. Okay. So let me recall you some of the many known results. I will probably, I'm missing several of them, but I just want to say something which are quite very fundamental for what I want to say at least. So in 94, Shandor Kovacs proved that the effective cone of a K3 surface is either circular or generated by negative curves. So there is no mixed behavior, at least for K3. So this is a partial answer to question number 2. In 2000, Nikulin proved that there are finitely many families of surfaces with polyhedral effective cone and such that negative curves have bounded self-intersection of given bounded self-intersection and bounded arithmetic genus. So this is quite important result, and also we are going to cite the same paper for another characterization of the pseudo-effective cone. Then Defernay in 2010 provided a picture and studied well, here I call it the Mori cone, but I have to say that, sorry for a surface, this is exactly the same of the effective cone, doesn't change. The effective cone of the blow up of the projective plane at R points in very general position is studied in the sense that he studied the position of the -1 curves, which are represented by the black dots in the following pictures. The 4 pictures are taken from the Defernay paper. The first picture is the very well-known one, is just the Defective surface. We are blowing up less than 9 points, so finite number of negative curves, and the convex hull of this is containing the cone Q. Then when you blow up 9 points in very general position, there are infinitely many -1, and they have a limit points in the anti-canonical. When you blow up 10 points, still infinitely many, but let me say that these curves, they lie on a cone of vertex -k. And finally, if you blow up more, then these curves, they go outside this tangent cone obtained from -k to the light cone. So the picture is a little bit different. So the big question is what happens in the unknown part of the effective cone. Unknown from the point of view of Mori theory. This is the part where classes have intersection product greater than or equal than 0 with the canonical. So it's exactly this bottom part. So there are 2 works which needs to be cited about this. First of all, Les Ultra in 2014 provided an example of an extreme array of f x10, of the pseudo-effective cone of x10, which is non-rational. So the coordinates of this divisor, they are in R and not in Q. This is obtained as an eigenvector of an isometry phi of the Picard surface. This isometry phi is just coming from Cremona, transformations of infinite order. So this is an isometry of the Picard group, which preserves the effective cone, also the light cone, also the net cone. And so there is using a theorem of Birkhoff, which says that if you have an isometry which preserves a cone, and then you look at the eigenvalues of this isometry, it has one real eigenvalue, which is bigger than 1, and all the other one have module less than or equal to 1, then the corresponding eigenvector is an extreme array of your cone. So in this way, you could produce this D, which is the eigenvector of this D lambda. And of course, the D which is produced here, it has an intersection product 0 with the canonical, because, I mean, phi is an isometry and dk is phi d dot phi k. It's because of these inequalities, and lambda is bigger than 1. So with this, he was able to produce an extreme array which is here and is irrational. And now, in this paper, which is, I think, quite important, by Ciliberto, Miranda, Roé, it's some weeks ago, they provided an example of D, which is again in pick real numbers. It's a rational class on blow up at R points. These R is for sure bigger than 9. They have several examples. R could be 13 and so on. This is again an extreme array of the pseudo-effective cone and of the light cone. But this time the ray has a positive intersection with the canonical. So they basically they use the kind of degeneration, which could be called the collision of fat points, but in the opposite way. So uncollision. So they reverse this degeneration, and so the idea is to produce a sequence of divisors converging to, for example, one of these eigenvectors found by Lesutre. In which way they converge? They start with something that they know very well, for example, a family of lines to one point, and then they apply this isometry field. And eventually the limit is this eigenvector. But then on each one of these divisors, they apply an uncollision. And the effect of the uncollision is to produce a class which is of self-intersection 0, and all the multiples of this class are empty, and they can prove this by using this degeneration. So since you have, when you have a class on the, let me do this, you have a class here on the boundary of the light cone, such that all the multiples of this class are empty, then this is somehow on the boundary of the effective. And so it is possible to prove that this class is also an F, because if you have, because the effective contains the light cone, which contains the F cone, which is dual. So the two of them can coincide here. And so they have a limit of these classes of square 0, and this converges to the D that they are able to produce. That this time is outside. So they have found a point here. To what I can understand, they can find, of course, more than one, possibly infinitely many extreme arrays in this round part, but it seems to me that they cannot prove that this is circular. This still remain an open problem if a whole neighborhood of one of such extreme arrays is contained into the extremal part of the pseudo-effective cone. So the mixed behavior still remains open. Okay, so this is some panoramic view on what happens when you blow up the plane at general points. So now let me move to another type of blow up, which still produces very interesting examples, which is the case of toric surfaces. So to introduce these toric surfaces, I will try to use the most simple way, take a lattice polygon. So this is a polygon whose vertices have integer coordinates. And this is going to define a normal toric surface, which is just the closure of the image of a map from the two-dimensional torus to some projective space. And the map is, you take x, and this goes to the vector x to the p, where p is an element in delta intersected with the z2. Is an integer points of the point. Now, the fen, defining this toric surface, is the normal fen to delta, and it comes with an M-fold torus invariant divisor H delta, which is basically linearly equivalent to a hyperplane section of this projective space. So this surface comes with a distinguisher point, which is the image of the point 1, 1 in the torus, and this distinguisher point has rational coordinates. This is important in what follows. This is a point in the big torus orbit. So about the effective cone of a toric surface, it is well known that this is polyhedral. It lives in this real vector space of dimension number of edges of the polygon -2, and is generated by prime torus invariant divisors. Classes of prime torus invariant divisors, each of which corresponds to an edge of delta. So in a recent work, joint work with Anna Maria Castrovete, Genia Tevelev, and Luca Gaglia, we proved that there exists a lattice polygon delta such that the pseudo effective cone of the blow-up of delta at the general point, this general point E, is non-polyhedral for all but finite number of positive characteristics. Okay, so this is another way of producing these pseudo-effective cones which are non-polyhedral. And let me explain a little bit the construction which is behind this. So I'm going to divide the proof basically in two parts. First of all, I will focus in case of characteristic 0, and then I will discuss positive characteristic. So one ingredient before entering the proof is the following. If I have X, which is a normal Q factorial projective surface with picker rank at least 3, so this is used for guaranteeing that the light cone Q of X is circular. Then, if the pseudo-effective cone is polyhedral, we have two conditions. First of all, the pseudo-effective is generated by finitely many classes of negative curves. This is a criterion by Nikulin, and in particular, this implies that the pseudo-effective of X is equal to the effective cone, because it's generated by classes of divisors. And the second observation is that if C is an F-divisor of set intersection 0, then C orthogonal is in the relative interior of a facet of the pseudo-effective cone. Well, the reason for this is quite easy. This is our Q of X. This is the class of C. And of course, this is an F class, so we may do C orthogonal. C has to leave the whole light cone from one side. The effective cone, the pseudo-effective cone contains Q of X, and also the pseudo-effective cone has to stay on one side because we are assuming that C is F. So this means that being by assumption the pseudo-effective polyhedral, it has to be something like this. And in particular, here we have a facet. This is a facet. C orthogonal is cutting out a facet of the pseudo-effective cone. And again, since the pseudo-effective has to contain Q of X, then this class has to be in the middle of this facet. Well, if we analyze the situation, this facet will be generated by some extreme arrays. They are here. These are classes of negative curves, which I'm denoting by Ci. So this means that the class of C is a combination, linear combination with the positive coefficients of the class of some of these Ci, because C lives in the cone generated by these classes. And after cleaning up denominators, I get that n times C is linearly equivalent to a sum with positive coefficients of these Ci, where these Ci are curves irreducible, which are in C orthogonal they are distinct from C, so they are disjoint from C, zero intersection. In particular, a strong consequence of this is that if I consider the restriction of NC to C, then this is going to be exactly the restriction, isomorphic to the restriction of this one. And since these Ci are disjoint from C, then this is OC. Okay. This means that OC of C must be torsion. So it is a consequence of the fact that the pseudo-defective cone is polyhedral. Well, then one construct the following example. Take lattice polygon with volume a square and number of boundary points, just the number in this case 5. So I have these 5 boundary points. And I take, this is going to define a toric surface P delta together with an ample class H delta. And then I take X, which is the blow up of P delta at this general point. And I take C, which is an element of the linear system pi star of H delta minus 5E. So this pi is just the blow up of P delta at the point E. So I take an element of this linear system. This means that you start with Laurent monomials given by these integer points in the polytope and impose a point of multiplicity 5. You can solve the system and you get the defined equations for the curve C in the torus is this one. So this is a curve which has a point of multiplicity 1 at 1, 1. A point of multiplicity 5, sorry, at 1, 1. So if you look at the defined polynomial of this curve, you can see that there are some red monomials. Those are the monomials whose exponents are vertices of the polygon. For example, this one is the vertex 5, 1. It's this vertex. And this one is the vertex 4, 4, and so on. So the fact that the Newton polygon coincides with the Newton with delta implies that C is a Cartier divisor in X. So we have a Cartier divisor. You can analyze this equation given here, deducing that this is an irreducible curve, and after blowing up the point 1, 1, the strict transform is smooth. Then we get the irreducible curve, smooth, and the two numerical conditions that we put before about the volume of delta, which was square, and the number of points on the boundary, they translate into this. So C is a smooth genus 1 curve, which is a Cartier divisor in X. This curve C has rational points, mostly because, for example, this edge has integer length 1. So this implies that this edge it corresponds to a torus invariant divisor of the surface. And the fact that the integer length is 1 implies that this is intersecting the curve C at 1 point, which is rational because the divisor is defined over the rationals. Okay, so actually C is an elliptic curve. Here is a minimal equation, and you can find this curve in the John Cremona database. The model by group is free of rank 1, and the restriction of C, which is of C of C, is an element of peak 0 because C squared is equal to 0, but it also has rational coordinates in peak 0 because C was an element of this pi star of H delta, and H delta is a torus invariant divisor, is defined over the rationals, minus 5 times E, and the E is the exceptional divisor over a point with the rational coordinates. So again, E is defined over the rationals. So we have an element of this Mordell-Weil group, which is known to be Z. So there are two possibilities for this restriction of C. Either it is trivial or it is non-torsion. The first case, it is easy to see that the curve C should move in its linear system, or that is the dimension of the H0 should be bigger than 1. But this is not the case because, let me go back, when you try to solve the linear system of these monomials imposing the point of multiplicity 5, you only get this. This is solution of a linear system. So actually this implies that the dimension of this H0 is equal to 1. And so this implies that the restriction of C must be non-torsion. Then by applying the previous criteria, the pseudo-effective cone of X cannot be polyhedral by the proposition that I showed you before. So the proposition was this one. If the pseudo-effective cone is polyhedral, it was given here, then we deduced that the restriction of C must be torsion. Okay. Okay, so this concludes the example in characteristic 0. In positive characteristic, it is more complicated because the restriction of C is always torsion. So we cannot use immediately the same analysis. So let me go back to the criterion, especially part 2 of the criterion. What we want to show is that this is not possible because there are not enough negative curves in C orthogonal. So we cannot write C as using these curves. So this means in some sense to be able to control negative curves into C orthogonal. We are not able to control these curves, but it is possible to move to another rational surface, which is anti-canonical, and there we can control these curves. So this is the construction that I'm going to explain now. So positive characteristic, let me start with this other lattice polygon. It's a bit more complicated than the one we had before. So this time we have 1, 2, 3, 4, 5, 6, 7, 8 vertices, but also 8 boundary points. And the volume is 64. We repeat the construction, same linear system. This time C is living in pi star H delta minus 8E. So the curve is irreducible, again, smooth, Newton polygon delta, and again, I'm not going to repeat, but C square is equal to C kx 0. So again, I can produce a genus 1 curve, which actually is elliptic, and this is as this label in the database, and the Mordell-Weil group is a Z plus Z4. And this time one can show that the restriction of C is a 4 torsion. I mean, this in characteristic 0. Okay. So now, what to do with this? First observation, the divisor Kx plus C is linearly equivalent to an effective divisor. This is quite simple to prove. You take exact sequence, defining sequence for C, and then you do tensor product with this divisor, you get the following exact sequence. This one by adjunction is OC. And since we are on rational surface, I mean, we are on this toric, blow up of toric, which is rational in particular, then H0 of the canonical and H1 of the canonical, both of them are equal to 0. Then you can, then this implies that these are sections. And since it is effective, one can apply Zariski decomposition and show that there is no positive part. So there are just negative curves. Some, let me say that I can write here Kx plus, plus C is linearly equivalent to some negative curves M1. There are coefficients also. A, S, and S. These are negative curves, and it is also possible to show that actually all the coefficients in this Zariski are integer. Well, in this case, it's effective, so they are positive integer. Then recall that C was orthogonal to itself and to K, so C dot Kx of C is equal to 0. In particular, C is orthogonal to each of these Ni. So when I do intersection product of this Ni with Kx plus C, this is just the intersection product of Ni with the K of X. One of these has to be negative because Kx plus C is a negative self-intersection, and this implies that we have a negative curve with negative intersection with K of X, so we can run this Kx plus C and NP and contract one by one all these N. So these are the contractions, and we finally reach a surface Y. Now, due to the fact that C was orthogonal to Kx plus C, so to all the Ni, this means that each Ni is disjoint from C. This is for all I. So I'm contracting curves which are disjoint from C. And this implies that I have a copy of C as a Cartier divisor on Y. On the other end, since I contracted all Kx plus C, now I have that on Y, Ky plus C is trivial. So minus Ky is linearly equivalent to C, which is Cartier. So this implies that Y is a surface which has at most dual singularities. And moreover, minus Ky being equal to C has the same self-intersection of C, which is 0. This is as remaining unaltered because I contracted things which are orthogonal. So we are on a rational surface with the dual singularities and anti-canonical class, which is NEF. So the theory of such surfaces is very well understood. In particular, if I do a minimal resolution of Y, I get a surface Z, which is smooth. Again, this pi is a Crepant resolution because the singularity are dual. So I have that the anti-canonical of Z is again linearly equivalent to this copy of C that I have also on Z. And it has self-intersection 0, so Z, I don't know if I wrote it, Z is blow up of P2 at 9 points. These points could be in special position, infinitely near, I don't know, but it's this blow up of P2. The anti-canonical is NEF, and then one can use a little extension of Mori theory to show that this time the pseudo-effective cone of both Y and Z is polyhedral if and only if this C orthogonal or K orthogonal is generated by classes of negative curves, which in this case are -2 curves. So right before this was a necessary condition for the pseudo-effective cone to be polyhedral. Now it also sufficient because the anti-canonical is net, and we know a lot more of this. In particular, since this pi is a resolution of dual singularities, so it's contracting -2 curves, then one can show that the pseudo-effective cone of Y is polyhedral if and only if the pseudo-effective cone of Z is polyhedral, and both conditions are equivalent to the fact that this KZ orthogonal, which is C orthogonal, is generated by classes of -2. So then one focuses on the last condition, which is more easy to manage. And the observation is the following. So first of all, let me start with the class of a -2 curve. Then it has a self-intersection -2, orthogonal to canonical, and restriction. This res is a restriction to C. And trivial restriction to C because it's disjoint from C. The interesting thing is that one can prove that a class which satisfies these three conditions is effective. So it is union of -2 curves because there are only -2 curves in this part of the pseudo-effective cone. The only reducible are -2 by adjunction. So I just have to check how many of these classes I have. And there is another observation which helps in doing this work. The observation is the following. If I replace R with R plus a multiple of C, then the first two conditions are going again to be satisfied because C squared is 0 and C dot R is 0. So C is orthogonal to such R. And C, of course, C squared equals 0 means, recall that C is linearly equivalent to K of C. And this is just C dot K of C. So the first two conditions are again satisfied, but the restriction can change because I'm adding this multiple of C. So with this observation, the only thing that I have to check is if I have a class satisfying these two, and such that the restriction of R is in the group generated by the restriction of C. If that is the case, then I can produce one of these sums where this restriction condition is satisfied. Okay, so how to look for these classes? The idea is the following. This KZ orthogonal is very well known. This is a lattice of type E8 tilde, E8 affine. C is in this lattice and it's orthogonal to everything. So I can do quotient by the C and I get a lattice of type E8. On the other hand, I have this restriction map, which maps to the restriction of any element in KZ orthogonal, modulo, in this case, the restriction of C. So one can show that whenever the restriction of C is torsion, this is our case now, because this was for torsion in the example. The fact that KZ orthogonal is generated by classes of -2 curves is equivalent to say that the kernel of this restriction is generated by roots of E8, just using the previous observations. So then one starts analyzing the example, computing these restrictions. Let me recall you that in our case, we have this elliptic curve C, and the restriction of C, it was for torsion, so it's a group with 4 elements, 4 rational points. I'm looking at the picture in characteristic 0. Now I take one root in E8, well, or the lifting of one of these roots into KZ orthogonal, so modulo multiple, and I take its restriction of this R, which is a point outside this group. This is in characteristic 0. When I specialize modulo a prime, since I'm saying that the 4 red points, they are distinct from the blue one, and this is going to stay the same for all but a finite number of primes, because the coordinates of these points are distinct in characteristic 0, so if P is big enough, after specializing modulo P, they are going to stay distinct. So this in particular implies that the situation is going to stay the same as for in characteristic 0 for all but finite number of primes. This because I have just to check finite number of roots, because E8 contains only 240 roots, which are finitely many. Okay, so a direct calculation shows that in this case, for any P distinct from the following, E8 is not generated by roots which live in the kernel of this restriction. And so for all these primes, both f of z and f of y are non-polyhedral. And this quite easily implies that also the pseudo-effective cone of X is non-polyhedral, because if you have a surjection of surfaces, then if the pseudo-effective upstairs is non-polyhedral, then also the pseudo-effective downstairs is non-polyhedral. Okay, so let me make a comment about this. I do not have time to enter this application, but it is possible to say, to prove that for surjections of normal projective varieties, not just surfaces, if the pseudo-effective cone upstairs is polyhedral, then also downstairs is polyhedral. Using this and the construction done by Castravet and Tevelev, we could prove as an application of this theorem that the pseudo-effective cone of M0 and bar is non-polyhedral for any n greater than or equal than 10 in any characteristic. Okay, in all the characteristic, but those displayed here, you can use the polygon that I showed to you, this one. And in other in the remaining characteristic, you are going to use other polygons. Okay, so all the polygons that we have used so far for this proof, they were they had at least 5 edges. In principle, it should be possible to produce example with the 4 edges, but we couldn't. And it is very hard to work with triangles. So let me say something about, to conclude about these other special polygons with less edges. So one interesting question is what happens when to the pseudo-effective cone of X when we are blowing up a toric surfaces which is minimal in the sense that it contains no negative curves. So it is easy to see that in this case either delta is a triangle or it is a parallelogram. So the case of the triangle has been studied a lot by several authors, but I have to stress mostly from the point of view of pseudo-effective cones by Gonzalez Anaya, Gonzalez and Calecaro. And in this case, let me say the following. So if delta is triangle, then the picker group of X is of rank 2. It could have torsion. The pseudo-effective cone is bounded by 2 extreme arrays. One is the exceptional, and the other one could be either the boundary of the light cone, which I'm denoting with R minus, or could be a negative curve, possibly, which is outside. While the light cone is bounded by these two rays, R minus and R plus, and I draw as a gray region here. In a recent work by Gonzalez and Aya, Gonzalez and Caro, they provide examples where this R minus has a rational slope and lives in the pseudo-effective cone, but not in the effective cone. So the effective cone is open on one side because no multiple of this R minus, no multiple of this R minus is effective, basically. So that there is a natural question, which is the following open problem so far. Is there an X such that R minus has an irrational slope and lies at the boundary of the effective cone? So the pseudo-effective cone in that case would be just bounded by this R minus, but this R minus would be irrational, so outside the effective, of course. This is quite important because such an example would imply, first of all, the existence of irrational Sechave constants, but then also in the case where, at least in the case where the Picard group has non-torsion, so when we are blowing up weighted projective, it would imply a non-trivial case of the negative conjecture by a theorem of Witkowski. So this has a strong connection also with the beginning of the talk, which was studying these blow-ups of the projective plane at points in a very general position. Okay, so let me say that, okay, if the other case, what about parallelograms? So if delta is a parallelogram, then in a joint work in progress with Luca Ugaglia, we show that the pseudo-effective cone actually is always polyhedral, and it is generated by the exceptional and classes of strict transforms of one-parameter subgroups. So the idea to prove this is to look for these one-parameter subgroups which produce negative curves on the surface. Of course, this will be negative curves having multiplicity, so intersection number one with the exceptional divisor, because this one parameter will pass through the point 1, 1 with multiplicity 1. So these are produced by, it is possible to prove that these are produced by some elements in the Hilbert basis of the cones of the toric surface. So the toric surface being a parallelogram, it is four cones. They are singular in general, unless the surface is P1 cross P1. And looking at the Hilbert basis of these cones produces these one-parameter subgroups. Some of them are negative curves, and we show that these are all the negative curves on the surface. In which way we can show that if we look at the classes of these curves, then the convex hull contains the light cone. And it is not difficult to prove that whenever you have finitely many irreducible negative curves, such that the convex hull of the convex cone spanned by this contains Q of X, then this your convex cone is the effective cone. So using this, we could prove this case. And finally, let me end up with just one example, which we don't understand. So the example is the following. take X, which is a blow up of a toric surface, which this time is defined by a fan and not by a polygon for a reason that I'm going to explain in a moment. The defined fan consists of the columns of the following matrix. So it is again 4 rays. So this could be the normal fan to a quadrilateral. This time the quadrilateral is not parallelogram. So the surface contains 8 negative curves, the exceptional divisor, 2 strict transforms of toric curves, 4 one parameters, and a curve of multiplicity 9 at E. But this time, if you do the convex hull of the classes of these curves, then it does not contain the light cone. You have something like this. So when you do the convex hull, this time you are cutting the Q of X. So this convex hull cannot be the whole pseudo-effective cone, and we have no idea what is going on here, if the cone has a mixed behavior or not. So one reason for studying this example is the fact that this Q of X is a circular cone, and on the boundary of Q of X there are no rational points. So if you remember in the example that I showed before, this theory that we did with Anna Maria Castravet, Geniatelle, and Luca Ogaglia, we started with the class C, which was a rational class on the boundary of Q of X, self-intersection 0. This example does not contain any such class. It's possible to study the conic and show that this has no rational points. And so there is no canonical polygon. I mean, there is no such polygon that we can associate to this, because that one was the Newton polygon of the C, and here we don't have a special polygon to represent this class of self-intersection 0. So it would be nice to understand what happens in this case, but this is completely open so far, and I think that I will just leave you with some bibliography, and that's it. Thank you.
Thank you, Antonio. Thank you very much. Let's thanks Antonio in Zoom like this. Thank you. And please ask questions. Okay, I have a question. I have several questions. So first question is, in the very beginning, you assume some constraints on possibly singular surfaces like Q factorial or something. But for example, on a surface, we can define the intersection theory and ampleness, everything purely numerical. For example, if you have some strange singular surfaces which are not Q factorial, and but is it difficult to study the cones? So maybe you have some pathologies or some.
I don't have a clear picture of this, because in this case the pseudo-effective cone could be, I mean, really bigger than the ample cone, because the ample cone could be lower dimensional because you have these singularities. And I don't know if you can, I mean, I always use this light cone, and the fact that this light cone has to be contained in the pseudo-effective. I think I'm going to lose this if I no longer have, I mean, if I have bi-divisors where I cannot take intersection. So I would say that I have no idea what is going on there, and which type of examples they can produce. Also, another quite clear reason for which we wanted to stay in the Q factorial is that we were studying the blowing up of toric. So due to this, we had Q factoriality. Yeah.
Yes. Okay. Good. And another question. So, for example, in dimension 3, what are the relevant results? Is it like a lot of studies?
This I don't know, because in that case, for example, this I think it's really open question, because I mean, of course, there are these results. First of all, there is a result by Mukai. If you blow up, for example, very general points in very general position in PM, no? Then polyhedrality of the effective cone has been studied by Mukai, and then by Kastravet-Tevelev. I mean, Kastravet-Tevelev, they also say that when the single effective cone is polyhedral, then in that case the Cox ring is finitely generated. So yeah, and I think that both results are not just for blow up of projective, but also for blow up of products of projective. But apart from this, I would say that not so much more is known. Well, some special blow-ups of P3 with computational methods have been studied, at least the Cox ring. But then also some. No, I know results for Cox rings. No, then I don't know in general if you start blowing up, then
I see.
Quite, yeah.
Okay, this is very interesting. So, any more questions to Antonio? Please feel free to ask now, or you can. Okay, maybe I stop recording so people feel more comfortable. Yeah.